Good afternoon, everybody. Welcome to Pathways to Electrification. My name is Robert Rennie. I'm President and CEO of Meditech Engineering. Over the last 5 years, Meditech has been in the development of a fleet, excuse me. Over the last 5 years, Meditech has been in the development of fleet optimization software for electric vehicles. Focused on underground mining, but adaptable to surface as well as other applications. Today, we will present the structure of the software with examples of actual results, and hopefully we have time for a short case study comparing our simulation results to real data. We hope to give you a sense of the complex factors involved when shifting to electric emissions technology, especially when it comes to a mobile fleet, and additionally when it comes to mining. Before I get started on the software description, let me explain to everyone a little bit about Meditech Engineering. We've been in business since 2003 and are focused on design, build, and testing of heavy-duty mobile equipment and subsystems. The industries we serve are underground mining, construction, energy, oil and gas, exploration, and geotech. Today, the reality is we are not just having conversations of EV and electrification in underground and surface mining, we're having it across the industries that we service. Meditech is fundamentally an engineering company, but we have two specialty divisions. One being the alt-drive division, which focuses on powertrain, electric powertrain development and system integration into all vehicles. And the second being our Borterra division, our specialty drilling division, which is focused on specialized drilling systems primarily for geotechnical applications. Calculating the return on investment for fleet electrification. Now that you understand who we are as a company, let's get into the details of some of the software. What is the cost of electrification is a question that we are constantly asked almost every day. We can look at this from a micro scale or from a single vehicle. We can look at this from a micro scale of a single vehicle to a macro scale of the resulting impact of full electric fleet on the site infrastructure. And ultimately, the cost per ton. And it's the cost per ton we really are looking to calculate. Here we will go through the process to understand the total cost of ownership compared to conventional solutions such as diesel. The electrification cost factors, we have broken it up into three specific groups. Production requirements, operating requirements, and the fleet requirements. The production requirements include tonnage, the timeline, and of course the production plan. The operating, and I'm simplifying this. Developing these inputs is a very complex and time-consuming exercise. The operating requirements being scheduling, infrastructure, availability, utilization, and the fleet requirements being vehicle sizes, energy storage systems, and powertrain models. You can see that some of the items are blue, some are green. The blue indicate fixed variables. The customer, the client, the mining company gives us the tonnage requirement and the timeline they want that tonnage produced. The green are variable. We play with them within the optimization software to end up with an optimized result. A good example that I like to use here is the scheduling. We can play with the lunch break in an underground mine through the shift. We can play with the lunch break to accommodate charging. We can shift things back later or earlier in order to get more productivity out of it. Vehicle sizes. We can try different vehicle sizes and different battery chemistries in order to obtain the optimum result. We call the software EVFOS, which stands for Electric Vehicle Fleet Optimization Software. It's a product of a multi-year collaboration between Meditech Engineering and McMaster University's Bauman Lab for Electrified Powertrain Research. The other thing I would like to suggest is this is the first time we've presented this after 5 years of work to the public. And we're just now comfortable enough with the results and the quality of the end product that we feel good enough about talking about it. The cost factors in the EVOS software are broken down into 3 modules. Submodule 1, which is the user inputs, which include mine layout, production plan, costs, operating parameters. Submodule 2, which is the vehicle model, which is something that we pride ourselves on being able to do extremely well, which includes the drivetrain, the energy storage system, and the fueling and charging. And submodule 3 is the simulation and optimization. Breaking each submodule down a little further, if we look at submodule 1, the mine layout, defines the duty cycles and the routes the vehicle must travel, obviously, from the mine geometry. The production plan impacts the number of vehicles required based on the tonnage and timeline. The costs include, again, keep in mind that this is extremely simplified. The costs are complex, but in short, include labor, fuel, energy, CO2 emissions, tax, if applicable, capital costs, etc. And then the operating costs, the shift length, frequency, brake schedules, etc. The submodule 2 defines the vehicle specifications utilized for the simulation. This can also be impacted by user inputs. Here, the client has the option of specifying an existing electric vehicle or fleet they would like to simulate, or we can take the existing diesel fleet if there's no options. We can take the existing diesel fleet and we can create electric digital models of those fleets, of those vehicles to use in the fleet analysis. But in short, the drivetrain, it includes the motor specifications, the number of motors. You may have motors on each axle, so there may be more than one. The gearbox and axle final drives, the auxiliary power requirements. The auxiliary power requirements are significant in EV operation, and that is the power required to do everything else other than the traction. So for instance, the power steering and the brakes. The batteries, it's our belief that there is no single battery chemistry that provides an optimum performance for all applications. Therefore, the optimization process helps us to identify the best battery chemistry for each vehicle, and they may not be the same. And of course, the charging type, battery swapping, CCS charging, MCS charging, high-powered charging, and so on and so forth. This is just a very simplified example of a vehicle model. I gotta get this button right. Yeah. So here you have an HMI user interface, charger, a source of fuel or energy. This controller usually houses the software which manages the power. We got a battery system. I'll come back and talk about this in a minute. Traction motors, gearbox, axles, auxiliary motors, inverters, and auxiliary pumps. So here is also a thermal management system that we find we have to include in the mathematical models. The facts are, and from our real-life experience, battery temperature is critical to optimum performance. Whether it's cold or hot, it doesn't matter. I was just at a site last week where it was 40 degrees with a vehicle that we built, and the battery temperature varied 2 degrees during a 13-hour day. The EVOS submodule 3 simulates and optimizes the vehicle performance based on the user inputs, vehicle models, and desired outcomes. It reads and formats the inputs as the inputs can be of various formats, but ultimately drives towards an optimization solution of the vehicle. This is again simplified. The vehicle performance, the mine schedule, optimized charging locations, and so on and so forth. Ideally, we want to drive to minimize the battery capacity and maximum vehicle performance, along with the mine schedule and the charging cycle. As one person told me once, we try and keep the operator in the seat. Simulation and optimization, this is getting into more detail on the simulation and optimization, on the steps within the process. So the first thing is the mine plan and the vehicle models have to be developed. This is an example of a mine plan. This one is came out of Deswick. We import all that data into the into the mathematical model. And as you can see, as you can see, this is a fairly complex array of drifts and stopes and whatnot. And it does get big and it gets complicated. The next step is to calculate the haulage distances and the grade profiles. This we usually produce in more detail, but just very briefly, you can see how the haulage distances are actually kind of building up. The high haulage distances are building up in this kind of area. This is the distance, this is the operating years, and this is the operating levels. And you can see how the production is driving the distances. The next thing that's calculated is the energy per cycle. Again, this is a fascinating piece of visual. Here's the energy kilowatt hours, operating years, operating levels, and you can see it does very much mimic, as you would expect, or mirror, as you would expect, the haulage distance map. The next thing that we produce is the SOC, or the state of charge. On this graph, we've got SOC percent here, time and hours, so this is a shift. This is all driven by inputs. You can see this line is wavy. Each wave is, I believe this is a loader working from the draw point to the remuck. But it could be an ore pass, but it doesn't really matter. There's about 25 cycles here. The operator stops for lunch. He charges for an hour. There are no breaks. He charges for an hour, and he continues on and does about 16 further cycles and finishes his shift here, and he plugs it in again, and he charges during the shift change. So that state of charge is driven by the vehicle model and the duty cycle. And again, we calculate this for every vehicle and every duty cycle. So you can imagine the amount of data that's created. The total energy required, and this is probably the most telling visual that I can put up. This is the total energy that is consumed. I believe this is just the haul trucks. Over the life of mine, this is in megawatts, and this is operating levels. This is life of mine. This is where the energy is consumed, or where the energy is consumed to move the ore from the level. And you can really quickly begin to see whether this, and I could be wrong, this could be the loaders, doesn't really matter. But you can really see where you need to start to think about where you need to put your charging technology, whatever it may be, fast charging, CCS or battery swap. And I've done several of these analysis, and there is no right answer. There's no one answer that solves all these problems. And then from there, we can calculate the fleet size based on the total energy. And you can see this fleet size, whoops, let's go back. This is actually haul trucks, and it's calculating the number of trucks. And the client can use this data to plan his capital expenditures on the fleet. So although the simulation results are fascinating for engineering and operational teams, understanding the total cost of ownership is critical for us to help us make these decisions. So calculating all the costs, we've calculated the energy consumption, and we can calculate the emission reductions. The energy consumption, evaluated energy consumption or cost over a specified time period, over life of mine. Reduce carbon tax, reducing the CO2, ESG savings. There's other savings that we could list here. I'm just trying to keep it at a level that I can get covered in the time I have. And the cost, the OPEX and the CAPEX costs, the vehicles, the charging capital costs, the maintenance and replacements, it all feeds into the total cost of ownership. That brings me to the total cost of ownership. This is an actual example that we did. There's a lot of numbers here. I don't think we need to look at them in a whole lot of detail. I want to point you to a specific one, but let me go through this a little bit first. It's a comparison of a diesel truck. First of all, it's a both on-highway haul and an in-pit haul. And it's extreme. You can see the costs are high. It's an extreme case. It's 300 kilometers of total haulage out of the pit and to the mill. We used a maximum of 150 kilowatts of onboard charging. And the fast charging, I want to emphasize, we used a value that the maximum current the batteries could handle based on the batteries we chose. And that was about 850 kilowatts. 850 kilowatts. This was done over a year ago. And today, I think we've had, there's been presentations by other people that confirm that a megawatt of charging is available today. We didn't know that when we did this study, but we assumed it would be available soon. So just hunkering down into itemizing the critical item here is the cost per ton. $21.15 for the diesel, $26.55 for the onboard charging, and $16.99 for the high-powered charging. So there is a case that tells you that there is a viable path to utilizing electrified haul trucks for this application. Just quickly, we'll go through this case study, and I think what I'm emphasizing here, there's a couple points I want to emphasize. This is not a full return on investment study. This is a viability, a feasibility study. It's an on-highway, 100% electric haul truck. The client wanted to evaluate the feasibility of 100% electric, 45-kilometer downhill haul. He wanted to know how the technology would perform in their application and how it would impact their operations. I want to point out a couple things. This is the profile we were running. We were running from the mine full. This is a stretch that is about 10% grade. This is another 10% grade. And this is all downhill at about 10%. 40 tons payload. Our concern when we looked into this, our concern with this was being able to control the SOC to ensure that the batteries could deal with all the regenerative energy. Because if the energy doesn't go into the batteries as we hold that speed back, this is on a mountain road on hairpin turns, the maximum speed is about 45 kilometers an hour that the diesel trucks run. We really had to be careful with this. So our modeling of the energy required told us we needed, with including the working range of the SOC, 388 kilowatts onboard energy at 1C would do it at a charge rate and 2C at a discharge rate. Typically, if you don't know, I'm sure most people do, batteries don't have the same charge rate as discharge. We used two 360 kilowatt motors, continuous. That was about 940 kilowatts peak. We also used a 2-speed gearbox because we had on, if I go back, we really had to be careful with the vehicle being able to climb these two grades. They're steep. So our simulation results told us this, and the interesting part here is this section of the graph. This is unloaded, going up the mountain. This is a tractor trailer, tandem trailer, to the brake check, to the mine, charging for 36 minutes, okay? And then hauling out of the mine, up those steep grades, right here, to the brake check, and then the long downhill. This is the long downhill grade, and that represents about 30 kilowatt hours of regenerated energy into the batteries. And that was critical that we achieved that as a minimum to make this cycle work. So our idea is to use this information, the simulated information, but gather the data and compare the simulated to the actual data and refine our modeling. And that allows us to continually improve and sharpen the modeling convergence with the actual data. And that, I believe, is critical for this industry. We've got to get better at simulating. We've got to continue to sharpen our simulation, and we've got to continue to collect data. So in closing, steps to optimize electrification ROI. Gathering information, you better have patience because it's not easy. Running the simulation, determining the fleet design, moving to an optimized fleet design. This is an iterative process, and the software will do some of it, but at times you have to go and change your inputs and rerun the software. And then calculate the total cost of ownership. Pretty simple. Next steps for the industry. Operationalized EV mindset. So driving a diesel truck is pretty robust. You drive it, sometimes it breaks, but you typically drive it, you fill it with fuel, and you drive it some more, and then you fill it with fuel some more. An EV tractor or truck or vehicle of any kind has several things that have to be managed. It requires, and I believe we have to get used to simulation and analysis. We need data. And we need to work towards optimization in order for it, for the cost to be minimum, and the production to be maximized. Grid sizing, something that, again, we're asked, and we're not grid people, but we know if you look at the amount of energy that is going to be consumed if you electrify fleet surface or underground, if you're going to electrify fleet, you are going to have an impact on your grid. There is no two ways about it. You are going to have an impact on your infrastructure of your mine if it's a brownfield. And then what emerging technology is coming along 2030, 2035 that is actually going to soften the impact of this. And those are the things that I think at a 30,000 foot level we need to think hard about. We're at booth 22. Feel free to come and talk to us. Thank you very much.
Couple of questions from the app. What level of detail do you use in your battery degradation models?
So the battery degradation models, I mean, there are battery suppliers that we use, we work closely with. There are other battery suppliers we don't. They keep their degradation models pretty close to their heart. We've got a lot of experience with it. We rely on our partners, and when we don't have that input, we rely on our experience with batteries. As we collect data, we will be able to create our own degradation models, and they will only become better.
Okay. For your case study, what did you attribute most of your modeling errors towards?
Temperature. We modeled it at 20 degrees. When we ran that run, it was probably 10 degrees, 15 degrees. We don't know how much of an impact that had, but we do know wind resistance is a very difficult thing, and it's a very difficult thing to calculate with a tandem tandem trailer. And that's probably where most of our error occurred, was the speeds we were running at versus, the wind resistance.
Any questions from the audience? The microphone's going to come to you. Just wait, please, because otherwise it won't be seen and heard on the video. Thank you.
Just will add to that, the errors. We've got fairly specialized, fairly well-trained individuals studying this data, looking at where we did make the errors in our simulation. And we look at it all the time. We're pulling data off that truck now, and we're studying it every day. The guys really, they hunker down and study this stuff. It doesn't just go on it's not forgotten. It's studied every day. So.
Okay, hi. My name is Kent Warner. I'm with John Deere. I'm curious, in your case study, one of the things that immediately occurred to me was, what is the impact on the mechanical brakes? Or, you think about brake checks and things like that. Is there anything that was different in either the design of the vehicle or the thoughts about difference of the regenerative braking versus mechanical brakes, downhill? I'm just curious, how did that factor in?
Really, that's a good question. On that specific truck, the operator uses his brakes 10 to 14 times on a diesel machine. On that truck, he touches them twice. And we actually put a Telma on the truck for added safety, and he started using a Telma, for those of you who don't know, is an electric brake on the driveline. He actually starts using his Telma to slow him down, to keep the vehicle under control. One thing I didn't mention was ideally, we could absorb more regenerative energy if we had more C rate on the charge side of those batteries. We'd actually have better results than I showed you. because we would have recaptured all the energy. Right now, having to touch that Talma twice on the way down, he holds it for 10 seconds. I was just there last week. He holds it for 10 seconds twice. That's the energy he's losing, not getting in. And so that, if we did miss that one. We were hoping that we could capture it all, but we can't. I mean, it's a heavy truck.
Any other questions? Oh, there's one more here. Do you see the possibility of using batteries on large rotary blast hole drills, and have you done any energy mapping for drills?
We've talked about it. We've been asked about it. We haven't done any work on a large rotary blast hole drill. I mean, we have done work on them, but not from electrical drive perspective. But we are putting small drives on some small drills, underground drills now. We have actually just engaged in a project for a small, I think it's a blast hole drill for underground. So we are putting a drive on a small drill, but we have not done a big drill.
Anything else? Okay, thanks, Robert. We're breaking for half an hour for coffee now.